Hey folks, and welcome back. In this lecture, we are going to cover Module 0, Part 2, and this section is called Intro to Computing. So what we're going to talk about today is how computers have changed over the years and what are the different career paths that you can have in a computing field, what different options that you have. So the first thing to say is computers are ubiquitous, and what that means is that they're everywhere. It is very likely that wherever you are sitting right now when you're watching this video, you're probably surrounded by 3 or 4 computing devices. For me, I'm sitting here on a couch. I am using a laptop on my lap. That's one. I have a phone, which is a computing device. That's number 2. I'm sitting next to a television, which is a computing device. That's number 3. It's got a built-in computer. And I'm actually surrounded by light bulbs that are intelligent. So they're all little computing devices. There's also a little smart display over there, so that's number 5. And yeah, they're just everywhere. Every device that you own probably has a computer in it at this point. So why is that? Well, it's a couple of reasons. The first is that once you make something smart, meaning you put a computer into it, then all of a sudden there's all kinds of things you can do with it. So, 5 years ago, light bulbs were not smart. And then people started buying smart light bulbs. And that means that now you can communicate with your light bulb. You can tell it to turn on at a certain time and turn off at a certain time. Some of them allow you to dim. Some of them allow you to change colors. Some of them even have built-in cameras and all kinds of other things if you have a security reason for outdoor, and so on and so forth. So putting a computer in there just gives you a lot more options all of a sudden. And so because computers have become so cheap, and easy to build and small, they can be hidden in pretty much anything, and then the options for that thing become a lot larger. So let's talk about how we got here. So pretty much before 1970, nobody had a computer. Unless you were a large corporation or a government agency, it just didn't happen. And you might say, well, that's ancient history, right? I mean, this is 2022 or whatever year you're watching this video in. And you're right, that is a long time ago. It's about 50 years ago, but you have to bear in mind that they didn't really exist 50 years ago, except for in these huge government or corporate kind of settings. So it's kind of amazing that in 50 years, which is probably the lifespan of your parents, we've gone from computers didn't exist to they're literally everywhere. So let's take a particular example. In 1982, which would be about 40 years ago at this point, in 1982, you could purchase a particular computer called a Commodore 64. That's actually a little picture of it right up there. And this was one of the first computers that sold in mass to home users. And that computer had 64 kilobytes of RAM. It had a 1 megahertz processor, and it sold for about $600. And just to put that in perspective, your phone that you're probably carrying in your pocket probably has 4 1.2 gigahertz processors. So let me be clear, a 1 megahertz processor means that the clock moves 1,000,000 times a second. A 1 gigahertz processor means the clock moves 1,000,000,000 times a second. And when I say the clock moves, in each time the clock moves, it can perform a calculation. So this could do 1,000,000 calculations a second, which was amazing. Your phone can probably do 5 billion operations per second. The computer had 64 kilobits of RAM. Your computer probably has 6 gigabits of RAM. Kilobit, 1,024 kilobits gets you a megabit, and 1,024 megabits gives you a gigabit. So 64 kilobits to 6 billion is a big transformation. And the cost has remained pretty much the same. Those computers are pretty much the same cost as probably what you paid for your phone. I mean, obviously phones range. Some of them are cheaper. They can be as low as $200. Some of them can be as high as $1,200 or $1,300. But still, the point is pretty valid. So in that 50 years, we have seen a 4,800 time increase in processing power and a 93,000 time increase in memory in 40 years. That's really amazing. It means that depending on how old your parents are, they probably grew up in a time when nobody had a computer. And now everybody has a computer in their pocket. That's a remarkable shift in society in a very short amount of time. So how did this happen? How did we manage to do this? Well, it really comes down to a lot of continuous changes. continuous progress, effectively. Each year, companies figured out how to squeeze a little bit more processing power into the same space, and they were able to figure out how to put more storage into a smaller area. And as that happened, and it continuously got better and better, these additive changes eventually got us to where we are today. So there are different groups of people that are responsible for these different things. The first group of people to talk about are the electrical engineers, the computer engineers, and the physicists. These degrees are generally focused on hardware design. So to be clear, when I say hardware design, this phone or the tablet or the computer that you're watching this video on are all hardware. It's something that you can physically touch. So there's a screen, there's inside of it, there's a little processor, there's some memory, there's all these parts. And those parts have to be designed by somebody. So electrical engineers, computer engineers, and physicists are generally the types of people who do this. And these degrees are all offered at Kennesaw State. You can certainly get an electrical engineering degree, a computer engineering, I think it's called something slightly different, but it's computer engineering, and physics. And you might say, well, why is physics included in there? Well, it turns out that a lot of the challenge of building computers has to do with pushing electricity through wires at very high speed. And there are some physical limits to how fast we can do that. And so physicists are generally involved and work with electrical engineers to make those types of things. So these are folks who deal in computing, but they don't really have anything to do with software. Usually most electrical engineers write little to no software. Computer engineers are somewhere in the middle. They might write some very low-level software that controls the chip, but generally they're not writing high-level software, which is what we're going to focus on in this class. And the physicists generally write no or very little software. So my point here is there's entire fields of computing that have nothing to do with writing software, and that's a misnomer that a lot of people have, that everything to do with computing is people sitting there typing on computers with Kermit hands. So the folks who do the rest of it are generally the software designers. And the software designers might be computer science majors, they might be software engineering majors, they might be information technology majors, they could even be data science, cybersecurity folks, or math people. All right, so let's talk about these different degrees and what each of them does and why those degrees exist and how they're there. And we'll come to that in just a few moments. All right, so based on all of this, what does the future hold? Well, there was a person named Gordon Moore who in 1965, he observed that we were basically able to fit double the number of transistors into the same surface area every 2 years. And the cost of doing that was halving each one of those 2 years. So this rule that he observed became a law. It's not really a law. It's not like there's somebody enforcing it, but it's one of those things that has been true since 1965, which is that every 2 years, the capability of the computer has doubled and the price has halved. And that's really phenomenal. Like, there's no real other example in history where something has grown that quickly. But it is part of the reason why we have these computers everywhere. Gordon Moore went on to co-found Intel, which is a company that makes CPUs. And so we're going to talk a little bit more about that in the next lecture when we talk about hardware. So to phrase it as simply as possible, Moore's law holds that computing power doubles every 2 years while the computers continue to get cheaper. And this has been true, as I said, since 65. Now, in the more recent years, this has slowed down. And there are questions as to whether Moore's law are going to continue to hold up in the future. And the reason for this is because we've kind of hit physical limits. And we don't know whether we're whether we will ever be able to get past those limits. One of those limits is actually the speed of light. And you might say, well, what does that have to do with computing? Well, a lot of computer networking relies on transmitting data at high speed down a wire. And there are basically two methods for doing that. One of them is to transmit electrons down a wire. That's usually a copper wire. And the other way to do it is to transmit light down a glass tube, and that's a fiber optic cable. And so realistically, the fastest that you can transmit the data through that tube is at the speed of light. And even for the electrons, it turns out to be approximately the same speed as to how fast you can shove it down a wire. And so one issue is that there's a physical limitation as to how fast we can move data. As far as we know, nothing goes faster than the speed of light. The other problem that we've run into is heat dissipation, and we're going to talk about that more when we talk in the hardware section here in another week. But it turns out that pushing electricity through a wire generates heat. And one of the biggest problems that we have is while we could go faster with computings, we will melt the computer as we do it. So it's a balancing act between the speed and the performance and the amount of heat it generates. We certainly have cheap computers nowadays. So it's absolutely the case that you can go out and you can buy a Raspberry Pi for $35. And the crazy thing is that's a completely fully functional computing. Raspberry Pi was created by a group of people, I believe in the UK, who wanted to make computing accessible and easy for people to play with, even in underdeveloped or poorer countries. So a Raspberry Pi is a fully functional computer. It's about yay big, and it has on it HDMI ports to plug in a monitor, USB ports to plug in a keyboard and a mouse. You can buy it online, you can buy power supplies for it and little boxes to hold it and all kinds of fun stuff like that. And you can connect other things to it. So it actually comes with a set of wires that are a set of plugs that you can put wires into, and you can control other devices from it. The advent of this has really actually accelerated some of the smart home kind of things, because if you can put a little computer inside of something for $35, then all of a sudden, a garage door opener can suddenly be automated, or a gate can be automated and can be opened and closed by a computer signal. And so it just gives you all kinds of options. So Raspberry Pis have been remarkable in moving forward computing. They're certainly not the only ones. There are many other boards out there, but Raspberry Pi is the most commonly known of them. So certainly something to be aware of and something to go play with if you have some spare time and an extra $35. So what to do? What has all of this done to society? Well, this is an interesting topic, probably not one that we can spend a lot of time on here, but I just wanted to briefly mention that for the most part, computing has been a boom for society. It has made some things way more accessible, it has made things more exciting, it has made things easier, but it's also had some interesting side effects that are maybe not great for society, and so we'll talk briefly through those. But the first thing I would say here is there are entire courses that you may take later on in your degree, which are devoted to this exact topic. It turns out that just from a general standpoint, anytime that something major changes in the world, it has ripple effects. When people first were able to print books, that had ripple effects. When people first got telephones and were able to communicate over long distances or telegraphs, that had a huge effect on society. And cars had a huge effect on society. This is another one of those seismic shifts in society where people are having to grapple with all of the changes that are happening at a very accelerated pace. And it's not unusual when a major change happens in society that people push back. For example, when elevators first came into existence, there used to always have to be a person who manually operated the elevator. When you came in, they pulled the doors closed, they pulled the lever to make the elevator go up or go down. And for many years, elevator operator was a thing. Thousands of people worked as elevator operators, especially in places like New York and places that have a lot of high-rise buildings. And then at some point, they figured out how to automate that, and all of the elevator operators went away because there was no need for them anymore. But society had a really hard time adapting to the fact that there wasn't a human being in control of this device that's effectively held up by strings inside of a big empty shaft that can drop to the middle of the earth. And you can kind of see why when you think about it like that. You're putting a lot of trust into an elevator when you step into it. Um, and so the compromise that we ended up with is that if you've ever noticed, most elevators have a human voice that talks to you while you're in there. Floor 3, going up. And that's because people found that soothing. And it's kind of funny that it's a computer that's playing playing a human voice just to make the human feel more at ease. But it's simply because it's a major shift, and some people had a hard time accepting that shift. And this is going to be true with every major shift that happens in society. It has positive effects, which means you can suddenly build taller buildings and people can be closer together and you can be more dense, and that's probably better from a economic standpoint and from maybe a emissions standpoint and all these kinds of things. So there are positives in that, but there are also negatives to it, which is that it made people uncomfortable. So there you go. All right, so many things have been made better by computers. Some things have been made worse, and each of these shifts has a effect. So let's talk about the positive things. So the first thing is people can more easily and effectively communicate further away. So in this modern day and age, there's really no reason to not be able to communicate with somebody else. Obviously, we have telephones, we have video conferencing, we have social media. And the fact that everybody has a phone in their pocket means there's really no point where you can be unable to reach somebody unless they're just in an area that has no cell coverage or whatnot. But I mean, most of your life you're accessible. You can reach other people, they can reach you. And that really wasn't true. If you think back before telegraphs, if you didn't live within a mile of somebody, there really was no way to communicate with them. You got on a horse and you rode over there. You maybe did that twice in your life. So it's really remarkable how easy it is for us to stay in contact with people who are not close by. And again, all relatively recent. We have universal translation software. You can use Google Translate. There are other ones out there. Some of them have in-ear buds where you can actually hear another person speaking to you in another language be translated in real time in your ear. And when you speak, it'll give them back the translated version in their language. This means that all of a sudden people who don't speak a common language can communicate, which is amazing. Online ordering, gig economy make life more convenient. So things like Ubers and Lyfts, things like grocery delivery and stuff like this make it so that people who are having a hard time getting out for whatever reason, let's say a pandemic, but also just older folks who don't necessarily have the ability to get out and go places, or people who can't afford to go places, suddenly have options of being able to get there. So that's great. Computers deliver almost unlimited entertainment, streaming services, games. I mean, again, 100 years ago, your choices were play a board game, throw rocks. Like, what were your choices? There wasn't Netflix and Amazon Video and Disney Plus and Peacock and 12 other streaming services that have thousands of things that you can watch at any given moment, movies, television shows, and games that you can download from your phone or from your device. Like, all of that is new. That wasn't something that was around that long ago. Advancements in AI have helped many industries become more efficient. In medicine, they've led to all kinds of breakthroughs on problems that we've been struggling with for years. AI is an interesting field. It's artificial intelligence, and it's where a computer is able to make predictions based on things that it has never seen before. It's something that it's not as magical as it sounds, and you'll see as we go through this class that there are limits to AI. We'll talk about them to some extent, but at the moment people throw around the term AI like it is going to fix all problems in the world, and I promise you that's not true, but there are certainly ways in which it can be very helpful. One example in medicine is looking at a scan of somebody's body and being able to detect that something is about to go wrong with that person is something that humans are okay at, but we're not great at. You're relying on one person's eyes to be able to detect that. Whereas a computer can look at the same picture for thousands of seconds in its own mind, and it can detect things that we maybe wouldn't even notice. It can notice that all the people who have this particular lesion or this particular mark down here in the bottom tend to go on to have this problem later in life. And that's something that a human would probably never notice because they only see 1,000 of them a year, or maybe they see 10,000 of them a year, but the computer can see 1 billion of them a year. So it's very good at detecting patterns and helping to do stuff. And that's been helpful for all kinds of things, not just medicine, for like crime fighting, for people to automate assembly lines and make things faster and more efficient. All of these are things that AI can help with. So all of these are very positive things that computers have done with society. But as I say, there are also some negative side effects that it has done as well. So for example, it is eliminating jobs. Every time that we automate something and make something more efficient, the downside of that is there's generally less jobs in that field going forward. The example I gave a few moments ago is still valid. Like, how many people do you know that are elevator operators? Probably zero, but at one point in time, there were hundreds of thousands of them. We are very, very close to automating driving. We have a number of different companies out there who have various different states of autonomous driving that they have completed. There are some autonomous taxis running around in some cities. And so we are very close to having something that can drive a car automatically. And the truth of the matter is there are thousands of people that are employed to drive vehicles. Truck drivers, there's 3.5 million of them in the US alone. And that doesn't count delivery drivers like UPS and FedEx folks and people who drive taxis and people who drive for a living. So as we automate cars, entire chunks of society are going to get laid off and they're going to have to find new work in a different direction. And so that's just something to be aware of. Um, I'm not saying it's necessarily a bad thing because maybe they can learn a new skill and they can go do something else, but it is going to cause a shift in society where those folks are going to have to learn something new and do something different. And there is definitively a possibility that we automate so much that eventually it gets to the point that no one has work. There are people working on automating coding so that computers can just code for themselves, which is a little terrifying, but there you go. It is a possibility someday. So that's one set of problems. Another set of problems relate to the fact that we haven't really figured out how to live in a world where we're so fully connected. The fact that we have phones in our pockets and we have something to look at all day sounds great, and it is great. It's very convenient. But it's having some mental health issues for folks as well, where people have had increases in depression, increases in anxiety that really weren't there 20, 30 years ago before we got to the point where everything was fully connected. And it's not necessarily that the phone is the problem, it's just that we haven't learned how to work with it in a way that is balanced so that it works for our lives. So these are a couple of possible things to be aware of that are effects that computing are having on society. Most of them are positive, but there are definitely some where you could question, well, maybe is it exactly the right answer, or are we moving in the right direction from a societal standpoint? And all of that needs more study. And again, this is as much as I can cover in this class. This is really an entire topic that could take a semester to discuss. All right, so let's talk about the different kinds of computing jobs. So the first thing to say is that you'd be very hard pressed to name any job that does not use a computer in some way. Like, people will normally say, okay, well, if you work in a grocery store, you don't. Well, that's not true. People who measure deli meat have a weighing scale, which is a computer. People who do checkouts do that with a computer. People who are putting stuff on shelves are usually using a handheld barcode reader to barcode them in and barcode them out for their inventory system. So there's that. Garbage collector people, you might say, oh, well, they don't use computers. Yes, they do. They use it inside the truck to decide where their route is and which houses they're supposed to pick up from and measure how much is coming out of each house and all that kind of stuff. So computers are just truly in every job. You would be very hard pressed to find a job where you don't touch a computer. So that's one thing to say, is that use of computer is going to be ubiquitous. If you want to be more directly involved in creating and building stuff for computers, there are different fields that you might want to consider. And this is something that most people don't really understand. They think that as far as computing is concerned, there's really only one path, and that is to write software. And the reality is, it's absolutely not true. Computing has all kinds of different fields that we're going to talk about. So the first thing to say is that the act of writing software, and I said this in the welcome video, is not actually something that is done with somebody coding for 8 hours a day. There is no job, for the most part, where you wake up first thing in the morning and you sit down at a computer and you start writing code and you do that for 8 hours and then you turn off the computer and get up and do that again the next day. That job does not really exist. Even a developer who is a high-level developer, they may write code for 4 or 5 hours a day, but the rest of the time they're going to be spending figuring out what code they want to write, talking with other developers in their group, deciding on what features they're going to implement, coding, documenting, testing, working with project managers and project managers to figure out how things are going to get done and prioritizing things. All of that is not really writing code. So even a full-time coder isn't actually going to be a full-time coder. So let's talk about the different degrees that we offer here at KSU, and let's talk about what each of them does and why they're different, because there's usually a lot of confusion about these different topics. So the first one is computer science. This was the first computing degree that most universities offered. When I went to college, this was the only computing degree that you could get if you wanted to do software. There was computer science or there was nothing. So it is the most common one that you will see at most universities. Computer science technically focuses on the theoretical aspects of computational thinking and problem solving. It is not really about writing code, it's about figuring out how to write code more efficiently, more more accurately, and to get things done in the best possible way. It's actually more of a theoretical degree where you discuss how things would be done rather than a practical degree where you're actually doing it. That's not to say that if you get a computer science degree, you won't write code. Probably the chances are you're going to end up in a job where you write code. My undergraduate degree, was in computer science, and for the 18 years before I came to KSU, when I was in industry, I wrote code a fair amount of that time. So that is a path. If you are really enjoying the coding aspects of this class, then computer science may be a great choice for you. Um, Computer science is very related to math. As a matter of fact, there's usually a lot of crossover between the two. Folks who start off in math degrees sometimes end up in computer science. People who do computer science degrees sometimes end up with minors in math or transfer over to math because they end up enjoying it. Because it turns out that a lot of how you think about computing and how you think about solving math problems are actually quite related. So, computer scientists are often spending time thinking about new languages, writing in new languages and creating new languages, and how to make new languages more efficient. They talk about how to make a language work better. They talk about writing new development environments or compilers. They talk about all of how you put together the infrastructure necessary to be able to develop. So, a typical job that you might get with a computer science degree might be a developer, which is somebody who predominantly writes code, but as I said, has other things going on. An architect, which is something that a developer eventually grows into if they are good. A good developer might grow into an architect such that instead of actually writing code, what you do is you describe what code is going to be written and you hand that to developers who are below you who do the actual coding for you. The architect is responsible for figuring out at the high level how the project or the application is going to be put together. Another possibility is a quality assurance person. Quality assurance in software is the person who figures out how to test that an application that's been built works correctly. So if you think about this, like any app that you have on your phone, somebody had to actually make sure that it works. And beyond just generally working, they actually had to make sure that every button press that you could possibly press causes the app to work in the way that you would expect it to work and not just crash or produce a wrong answer. So this isn't done manually. It's not like somebody is sitting there clicking every button on the screen. Usually nowadays, we write software that it's testing other software. So quality assurance folks usually are software developers that are writing tests to test other people's software. All right, so that's the computer science folks. The next group of people to talk about are the software engineering majors. So software engineering is more focused on the software lifecycle. What does that really mean? So we come up with a great new idea. I'm going to build an app that does X. And then I go off and I build that app and I put it out there. Well, it's not done the moment that I put it out there because usually what happens is within a couple of months, people are like, well, that's great that it does this and this, but wouldn't it be even better if it did this, this, and this as well? Or could you change this one thing so that it works like this? Or could you add in new things? If you think about writing a game, for example, on a phone, initially when you put it out there, people are going to play it and then they're going to get bored of it. And so you're going to have to introduce new things into the game continuously. So the software lifecycle talks about from the time that you come up with the idea to the time that you actually implement the idea to the time that you test that idea and make sure that it is working and doing what you hope to coming up with the next feature release, i.e., new features that you're going to add in there, back to the beginning again, where you implement those features, test them, come up with the next ideas, implement those, test them, come up with the next ideas, and then eventually there will come a point where nobody wants to use your app anymore because it's been replaced by something else. And in the case of an app on a phone, it's not a big deal. Usually you can just take it down and people will have moved on. But in business, if it's a piece of software that's doing something, you're going to have to replace it with a new piece of software that does that same thing and whatever new thing you wanted it to do. So part of the software lifecycle is how you remove a piece of software out of production, how you replace it, and how you migrate from one old system to a new system. So software engineering is more focused on that than on the actual software development. It's a study of how teams can work together to create large-scale applications. If you take a large company like a Microsoft or a Google or an Amazon or Twitter or any of these large companies, they have thousands of developers. It's not like there's 4 people that write the application. So how do thousands of people work together to build something that's cohesive? Well, they have to all be working on the same playbook where somebody has decided this is what we're going to build, and then they broke it down into chunks, and then this team works on that, and that team works on this, and then eventually they're able to put that back together again to make the final application. So software engineering deals with how does all that work? Like who decides who's going to do what and how we're going to do it, and what is the best way to actually get it done? There are many different software engineering ideas. So years ago, people used to mostly develop large-scale applications using something called the waterfall method. And the idea there was you sit down and you plan and you come up with exactly what you're going to do, and then you write a design for exactly how you're going to do it, and then you actually go off and you code it, and then you test it, and then you release it. And that process may take 2 years. But at the end of it, you know that you built what it is that you wanted to build. And the problem with that is software moves faster than 2 years. By the time the 2 years has gone by, whatever idea you had 2 years ago may or may not be relevant anymore. And so people have slowly moved away from the waterfall method and have moved to something that's called agile. And in agile, rather than deciding exactly what you're going to build, you just decide what you're going to build this week or this month. And then you build that, you test it, and you get it pushed out, and then you decide what you're going to do next month. It's a more incremental, smaller chunk kind of way of looking at things. So software engineering has all of these different methodologies on how to go about building software, building an application, eventually retiring it, getting new features out there, and so on and so forth. Software engineering also deals with how you maintain your code. As you write stuff, you're going to realize that you're going to have to change it. And when you make changes, it's possible you break things. So you have to be careful that as you're fixing things, you're figuring out how to integrate those things correctly into your software such that nothing is getting lost or broken as you work. Typically, software engineers write less code. So they're less focused on code writing than the computer science people. They're more focused on how the actual thing gets put together at a higher level. So typical jobs, developer is certainly on the list because you're capable of being a developer. But other jobs that have nothing to do with being a developer might be a project manager or a product manager, and again, quality assurance. So let's talk about product managers and project managers. A project manager in an organization is generally somebody who decides how we're going to get something done from beginning to end. So let's imagine that you work in a corporation and they're going to retire some piece of software. I'll take a simple example. They're going to upgrade every desktop from Windows 10 to Windows 11. Well, that's not something that you can just do overnight. It turns out you're going to have everybody back up their information on their computers. You're going to have to go through and do the install on each of them. You're going to have to figure out what software is installed on each computer and is it compatible with the new version, and so on and so forth. It's a whole project. So you would assign a project manager to break that project down into smaller tasks, have people go do those tasks, and then figure out what the timeline is going to be and how quickly you're going to be able to get it implemented. This is not somebody who generally writes a lot of code. As a matter of fact, most project managers would write no code, but they are part of software engineering organizations because they are the ones keeping track of where we are in each project and how stuff is moving. Product managers, on the other hand, are folks who look at a product that you're going to put out and decide how competitive it is in the marketplace. So I've got this great idea. I'm going to go build an app that involves walking around and catching cute little creatures. Well, a product manager is going to go, okay, well, let's figure out who the competitors for that are. Well, there's Pokemon Go and there's all these other games that are already out there. So what features do they have and what features are you planning on implementing in your game? How is your game going to stand out from all of these other games that are there? How much should you charge? How long should the game be available? Should people pay for it or should it be ad supported? These are all questions that somebody needs to go and research and figure out, and that would generally be the role of a product manager. So both of those roles are not software developers. They're folks who are figuring out how to put stuff out in the world, and there's a huge need for those roles as well. So if it turns out that you don't love coding, which that is possible, it's not for everybody, then there are still roles in computing like product managers and project managers and QA people who don't write code all day. They do some bits of it here and there, but they're more involved in bigger project-looking views of the world. All right, so the third major that we offer here at computers at KSU is computer game design. This is focused on the development of computer games. So to be clear, this is mostly focused on the coding side of computer games. There is also the graphical side, there is also the modeling side, there is the gameplay side, and so on. And we do touch on some of those things as we go through the program, but it's predominantly focused on how somebody can write a game. This is not something that a typical person does by themselves. Usually, game design is going to require a lot of people because today's games are pretty complex. We don't generally ship out, Pac-Man or stuff like that, which are pretty simple, and you actually could write Pac-Man by the time that you're through 1322. These are going to be more complex games where there's computers involved or AI involved on one side that you're playing against, or perhaps it's a lot of networking where the computers are talking to each other and you're involved in involving other players in the same game. So typical jobs that come out of here, you have game developer jobs, you have just regular developer jobs, you have architects, you have quality assurance. It is true that there is a smaller industry of game design. Not to say that there isn't a game design industry, there absolutely is, but there aren't millions of companies that hire game developers. There are a small handful of companies that hire lots of them, and then there's a large number of companies that hire a small number of them. And so it can be quite challenging to find a role in a game development company. So sometimes folks who come out with game design degrees don't directly end up working in a game design company. They actually may end up working in another company that's related, or in some cases completely not related. So the same skills that you learned as a game developer work in any other industry. And so sometimes people come out and they're like, well, this really isn't for me, or they don't want to work in it, or perhaps they can't find a role in it. And so they end up in other development jobs. Eventually they grow into architects and quality assurance people, the same as all the other folks. All right, so that brings us to information technology, or IT. The IT degree is more focused on how you maintain and deploy systems. It's not really focused on the coding part at all. As a matter of fact, most IT people only write small amounts of code. Pretty much everybody will write some amount of code. But if you're looking at this list, software engineers and information technology people are towards the smaller end. Game design and computer science people are towards the larger end from a development standpoint about how much code they might develop. IT people generally fall into a couple of different categories. Potential jobs might be help desk folks. These are like UITS here at KSU, where you can go and they can help you with a computer problem. That's a help desk. System administrators, systems engineers, database administrators, network engineers, security engineers. These are all folks who talk about individual parts of how the big system works. So you've got the software developers that are writing software, but that software eventually has to run on a computer. And if you're in a large corporation, those computers are going to be servers, and somebody has to manage the servers, not manage the software that's running on them, but actually manage the servers. When hardware dies, they have to replace it. When the server goes into production, it has to be connected to other machines, and that's done through the networking team. Very often, they store large amounts of information, and that's generally going to be done with the database administration team. And somebody has to make sure that all these computers are secure and that you're not getting hacked or broken into or malware put on them and whatnot. And that's going to be the security engineers folks. So again, IT, smallest amount of coding, but definitely involved in computing, just in different aspects of it. And I would point out here that some folks just naturally fit well in one of these categories. Some folks really enjoy the security aspect of things. Some folks really enjoy the networking aspect. Some folks really enjoy the database. I would encourage you to try each of these different areas because one of them may work really well for you. So that brings us to cybersecurity. So cybersecurity folks are the people who are constantly analyzing threats. They're dealing with security incidents. They're setting and enforcing policies. So what does that really mean? So if you have a large set of computers that are connected together in, let's say, a data center, then those computers are serving one particular application. And so if you think of like a game that you might play, there's some back-end servers that have to keep track of where everybody is in the game and what progress they've made and all of that. And so your computer at home is connecting to these computers that are in that remote data center. Well, the fact that you have thousands of computers all over the world talking to these computers on the back end means there's a potential security problem there because somebody can do malicious stuff and send bad information to the computers. And so a security engineer or a security analyst is somebody who will take care of making sure that all of that information that's coming in is appropriate, that there are no threats coming in, that the computers are not accessible in any way that they're not supposed to be accessible, meaning that you can't connect to the computer randomly. No one can push files onto the computer that might have malware or ransomware or anything like that in there. So it's a whole different field of computing, still has to do with computing, but it's more focused on how to protect large infrastructure computing in the real world. Um, Folks in cybersecurity also deal a lot with forensic analysis. So if a computer does get attacked, having to go through and figure out how the attacker was able to get in, figure out how to defend against that in the future so the attacker is not able to come back, figuring out how to undo what the attacker has done or write off the computer and decide that you're going to reinstall it because perhaps they did something that you can't detect. Looking at logs to see what happened, looking at information on the computer is all part of a cybersecurity person. And again, that's a separate specialty that we offer here. The data analytics or data science folks. All right, so data analytics is taking large amounts of data from the real world and figuring out how to extract information from it. So what do I mean by that? Well, every time you go to a store, whether it's an online store or an in-person store, and you purchase stuff, they keep track of the fact that you purchased those things. And the reason that they do that is because the store wants to know how much of everything to stock. So for example, if one week everybody buys, a large amount of Coke, then they need to stock more Coke, which means that they have to have deliveries of Coke that come to the store more often that week. And it may be that at Christmas time or at a holiday or something along those lines, people tend to drink more. 4th of July is probably a great example. People probably drink more soda on 4th of July. No idea. So a computer keeps track of what everybody's buying because that's useful for the store to be able to know what to purchase and how much of it to get delivered, because they don't want too much because then it's sitting in the back and it might go bad, but they don't want too little because then somebody might come in and want something and they don't have it in stock. So they want to have just the right amount. Well, by doing that, they're recording every single sale that happens. So now somebody might sit back and go, well, what hours should the store be open? And you could look at all of the data and you could decide, well, it turns out we sell the majority of our stuff from 10 a.m. until 3 p.m. So the question then would be, well, is it worth keeping the store open from 3 p.m. till 6 p.m.? Because if all of our sales are happening by 3 o'clock, then why are we paying people to stand here from 3 o'clock to 6 o'clock? And so this is the idea of extracting information from a pile of data. The pile of data is the millions of things that people bought. But the information that you can pull from that is, when is an appropriate time to have the store open? What marketing information can you get from this? If everybody who uses a credit card, it will record the name of the credit card with the sale. So that means that the store, like a grocery store, could look at that and say, okay, well, this person tends to buy dog food every third week. Can we convince them to buy the more expensive dog food by sending them some coupons? And we can do that because we know they have a dog and we know they're going to buy dog food on this Tuesday. So extracting information, figuring out that people have a dog or figuring out who the people are and when they come into your store and what types of things they want to buy, those are all things that data analytics or data science folks would look at. And this is a very trivial example. It can get a lot more complicated than this. So the data for data science is generally going to be huge data sets, looking at millions and millions of transactions and trying to find patterns in that or trying to find how you can answer interesting questions out of all of that. So data analytics folks will generally end up in jobs that are data analysts, business analysts, marketing, project managers. And again, it's because these are folks who are very specialized at looking at large amounts of data. Computers really facilitate that. If you think about an olden day, before a computer, the grocery store has no idea how often people buy things because they don't have a record of it. But computers make it very easy to have a record of it. Every time you scan an item across the scanner at the checkout counter, all of a sudden they know that. And if it's an online store, they know it from every transaction that goes on. This is why everything that you use, Spotify, Pandora, Amazon, grocery stores of any kind that you order stuff from online, or any store that you order stuff from, they can all give you suggestions about other things you might like. The reason they're able to give you those suggestions is because a data analyst has written software that looks at things that you like and looks at things that other people like, and then things that other people like that you don't necessarily see yet, it recommends them. When you go to Netflix, it's like, hey, you're probably going to like this show. And the reason is because other people who have watched the same shows as you and liked them end up liking that show as well. And maybe it's a show you've never heard of. And so that's a data analyst, a data science person. They go through and they look at that. And then the last group of people we're going to talk about are the computer engineers and electrical engineers. As I mentioned, these are people who decide how the hardware is going to get made. They design computer chips, computer circuits, computer boards. They may write some software, but it's usually the low-level software like the BIOS software or device drivers, and they're more related to the physics and the engineering of how stuff goes together. So if you think about your phone, somebody had to decide exactly what shape this is going to be, and it's not arbitrary. They didn't decide that it's going to be this shape because of some reason. They decided it because the particular components that had to go in here all occupy a certain amount of space. And this is the most pleasing form factor that somebody could come up with that holds all of those components in the shape that you can hold in your hand. So inside of here, there's a battery, there's a processor, there's a graphics processor, there's some memory, there's some long-term memory, there's your screen, there's the ports, there's the power supply that came with it that actually charges the ports, and then you might have auxiliary ports like microphones. There are sensors in here for how fast the phone is moving and which way it's oriented and which way is up and which way it's down. There are communication chips in here so it can talk to GPS satellites, so it can talk to Wi-Fi networks, it can talk to cellular networks. All of those components were designed by hardware engineers, and somebody had to figure out how to put them together so that they fit in this handy little container. So that's what a hardware engineer or a computer engineer or electrical engineer does. They generally design the hardware. So beyond all of those degrees that we've talked about, another path for folks is a management path. And the truth is, in the world of computing, it's quite hard to find people who are good at computing and also good at working with people. It turns out that we are all, and I'm included in this, folks who are computing folks tend to not be great at talking with other people. I'll let you decide how good you are at that yourself. But if you're good at it, then think about the folks that you sit around. So being able to work with others and being able to talk to them and being able to communicate with them is something that is a very learnable skill. It is something that you can figure out how to do. And if you're good at it, then another path for you, rather than being the person who actually writes the code, is to be the person who manages the other people who write the code. And so that's why we have management degrees and we have business degrees. It's for folks who want to be at the next level above the folks who are doing the actual coding, the project engineers, or the project managers, the product managers, the architects, the developers, the quality assurance people, the database administrators, the security people. There's a team of management that sit above all of those folks and decide at a very high level how we're going to get stuff moving forward and working with people to help them get their job done. And so that's another path, again, in computing that doesn't really have a whole lot to do with software development. So the point of all of these slides, the reason that we wanted to go through all of this with you is, the first thing is a lot of people don't understand the difference between each of those paths. And so I wanted to spend a little bit of time talking about what each of those paths might be, because some of them may be more interesting to you. Don't feel like you have to do the thing that somebody told you to do. Figure out what's interesting to you, try each of the things, and then make your decisions based on that. The good news is, no matter which one of these degrees that you get, if you're in a computing field, the chances are you're going to be able to find a job without a problem. This is a very good career path. There are plenty of jobs out there for people who understand how to code, understand database administration, security, project management, product management. These are all fields that are hiring lots and lots of people at the moment. So the job prospects are good, but it's important that you find a role that you actually like. Don't do it just because of the money, because honestly, that's not going to work out. You're going to be miserable. So make sure that you find a job that you enjoy doing, a task that you enjoy. And one of those fields that we just talked about is going to be more interesting to you than another one. For me, my master's degree was in information security. It turned out I really like the security side of it. I also very much like the database administration side and the coding side to some extent. Now, it's ironic because I teach coding all day long. I'm capable of doing all of the various different things, but for me personally, I enjoy some of those things more than I enjoy other things. And that's going to be true for you as well. Probably not the same set that I enjoy. That's what makes us all different people, right? We enjoy different things. So it's important to be able to think through different things and try different things and then see which one works for you. Across all of these fields, the one thing that is common is going to be your ability to problem solve. Whether you are a security person, whether you are a database administrator, whether you're a product manager or project manager, whether you are somebody who is in Helpdesk, whether you are somebody who is in management, in all of those cases, you are going to have to be able to problem solve. You're going to have to be able to take something that's very difficult that you don't know what to do with and figure out how to solve it. So that is the most important common element across all of these degrees that you want to think through and figure out how you can learn, because that is the thing that's going to make the most difference in your life. It all is about using algorithmic thinking, which is breaking a task down into smaller, more manageable tasks and figuring out how to make a computer do the thing that you want it to do. So, problem solving. You learn nothing from success, only from failures. It is a critical aspect of problem solving is failing. You must be willing to fail. And that's a really weird thing to say, because in every part of your life you've always been told, don't mess it up. Well, welcome to computer science. Please mess it up, and then learn what was wrong and try something different. And along the way you will learn, oh, I can use that for that, and I can use this for this, and this doesn't work at all, so I should never do this again. And that's actual learning in computer science, in software engineering, and in all of these fields. It's trying something, it failing, and being willing to try it again. Do not give up, just keep trying. And I will say that I constantly get told this: failing is disheartening. I have people come to me every semester and say, I just don't get it. It's never going to make sense to me. I'm never going to be able to do this. And the answer is, yes, you can. Yes, you will. You just need to keep trying. Stop worrying about the fact that you're not smart enough or you're not going to be able to do it. None of that matters. Just get up and try it again. And if you keep trying it, you will figure it out. Ask questions, come to the live sessions, ask your instructor, keep asking questions until you understand it. All right, so how do you fix a big problem? You start working on it, you ignore the parts that you have no idea what to do with, you break it down into smaller problems, you start to solve the smaller problems, and you work your way back up. And when you get stuck, you ask for help, and most importantly, you don't give up. So, what I would like you to do is to think about this. Go build an electric car. I'm not actually telling you to go buy all the parts, but think about how you would go about doing that. And the answer is, you don't know. Unless you happen to work for an electric car manufacturer, you probably don't know how to do this. Nor do I. And that's the whole point of this problem. It's not for you to tell me I don't know how to do this. I will never be able to figure this out. I am not a car manufacturer. The point of this problem is to take that big task and break it down into smaller, more manageable parts. What do I mean by that? Well, what are the parts of a car? Well, there are wheels, there's some kind of a body, there's some kind of seats, there's some kind of engine or device that is propelling the car. If there's going to be a motor, it's going to need a battery. There's going to be headlights. There's going to be windows. There's going to be storage space. There's going to be an onboard computer that you can play music on. Okay, now that we've broken that down into smaller things, you will quickly realize some of them you've no idea how to do, and others you actually probably do know how to do. I suspect you know how to make a wheel. It's round, and it usually has some form of a tire on the outside. So while I am no expert in wheels, I'm pretty sure that I could figure out how to make a wheel. I don't know all of the details, like what particular metal should I use, and exactly how big should the wheel be. The simplest answer is probably go see what size tires are available and use an existing tire that's out there in the world. And then figure out how to make the center part that holds the tire. How do you attach the tire? I have no idea, but I do know that there are people down the street who know how to attach a tire to a wheel. So I'm going to go ask them how to do that. Or I'm going to bring the tire and the wheel to them and say, please attach this wheel to this tire because you're the expert on this matter. And so on and so forth. How do I build the body of the car? Well, I don't know off the top of my head, but I can tell you the basic shape of how a car looks, so I could probably figure out what all the bits are that need to be attached to each other, and I know that metal can be welded to metal, so assuming you're making it out of metal, then effectively you find all the bits, and then you're going to figure out how to weld them together into the appropriate pieces in order to build the frame. And so I could spend a couple of weeks and I could figure out all the bits, and then I could figure out how they attach together, and maybe I use some kind of 3D software to be able to put those together and figure out how that works. And then I'm going to have to continuously change that, because when I decide where to put the wheels, it's going to matter how big the wheels were. If they were really tiny little wheels, that's going to work very differently than if they're huge honking wheels. So we'll have to keep modifying that as we go, and that's okay. My point here is we don't know the answer to this question. Nobody knows the answer to this question. Maybe Elon Musk. But most everybody else does not know the answer to this question. So the answer is you break it down and you find the little bits that you do know how to solve and you focus on them. And when you have solved them, that will give you hints as to the next thing. The fact that you now know how to build a wheel means that you can understand that there has to be something that holds the wheel. And that has to be attached to the car somehow, otherwise the wheels are just going to roll off. And so you can start thinking through the next part of how to solve the problem. And with enough time, you can design your own car. You can design your own airplane. You can design any piece of software that you want to write. You just have to break it down into the manageable parts and solve them. So that completes today's lecture, and that is module number 0. We're going to pick up at module number 1 in the next video, and I will see you there.